Hi guys, got a quick video here. Sorry I haven't posted in a while, I've been quite busy. But this is basically everyone's least favourite topic. And to be fair, I can understand why, because it's quite difficult. But it's analysis of an unknown organic compound, which involves NMR, IR, stuff like that. The first thing I would do is focus on the NMR peaks. So you've got these four here. This is the integration of these. So you can see here, this amounts to 4 H environments, like so. This is 1, this is 3, and this is 3. So total is 3 plus 3 plus 1, which is 7, plus 4 is 11 hydrogens. But that's only in D2O. If there's an OH group, for example, there could be 12, 13, etc. But any non-NH or OH hydrogens, there's 11 of them. So now I know all those non-OH and NH hydrogens, I'm going to focus on the elemental analysis by mass up here. So we know 73.1% is carbon, 7.3%, I won't read out the rest, but you know that. So that means we can write carbon here, hydrogen here, and oxygen here. And we know that essentially the mass is going to be equal to 73.17, 7.32 there, and then 19.51. You're then going to want to divide these by the MRs, so, or the ARs, sorry, the atomic masses. So 12, 1, and then 16. And if you do this, you get an answer of 6.1, 7.32, and then 1.22. And this is basically, this isn't your ratio, but it's very close. You have to choose the smallest one here. So as you can see, the smallest one is 1.22. So these are basically the moles of carbon, hydrogen, and oxygen. And so you have to choose the smallest one for the ratio. So if I now put R here for ratio, this would be 1. We just assume that this is 1. This is worth 1 part. And then what you want to do is divide this by 1.22 and this by 1.22, which comes to roughly, it's always going to be approximate, but this is roughly 5. This is roughly 6. If you imagine that this is about 1.2, 6 divided by 1.2 is 5, 7.2 divided by 1.2 is 6. So roughly, it's going to be C5H6O is the empirical formula. The MR of this is going to be equal to 12 times 5 plus 6 plus 16, sorry. This will be equal to 82 grams per mole, like so. And this, the actual MR, sorry, of the whole compound, we know from just here. The molecular ion peak is 164. That, 82 here, is half of that. So you know the actual molecular formula is going to be double this. So it's going to be C10H12O2. This then briefly leads me back. As you can see, 12 H's, but over here we found that 11 H's were made. Sorry, not made in the NMR, but only in D2O. So we know, as there's no N's, there is going to be at least one OH proton there. Also, when you look at this IR, there's not much to it apart from 2 major things. This is going to be a carboxylic acid group, because it's very wide here, very broad peak around this region, which if you look at the IR sheet, like so, you can see that the broad peak here, 2,500 to 3,300, is carboxylic acids, which is this area here. And this very harsh peak at about 1,700, this can only be a carbonar group. 1,700 is within this range, sorry. As you know, it's a carboxylic acid group. There's only 2 O's in a carboxylic acid group, which also checks out for the molecular formula here. Now focusing on everyone's favourite part, obviously the NMR, because it's never great to be fair, but this bit should help you. You can see over here, the range is probably, it centres where it's hard to tell because it's very wide, but it's about 7.0 to about 7.5. If you look up here, it's almost always going to be an aromatic hydrogen there. So you can assume that there's 4 aromatic hydrogens. So therefore you can assume, not entirely sure where, but for example, it could be an H there, it could be an H there, could be an H there, and could be an H there. But there's going to be 4 of them. Not 5, not 3, just 4. Over here it's a bit harder to tell because this is around, this would be about 2.4, and this will center about 2.7, for example, both of which fall within this category up here. So it could either be an H bonded to the carbon, bonded to the aromatic ring here, or it could be an H bonded to a carbon, bonded to a carbonyl. It's hard to tell at the minute. One major tip I would say for it is you can see 3 hydrogens are present in this. And so you can see it's either going to be CH3 bonded to an aromatic ring, which is very much likely, because I'll explain why, or a CH3 bonded to a carbonyl. But we know that it's COOH, it has to be a carboxylic acid. So if it's a carboxylic acid, it'd be CH3 here, and then the C double bond O, and then an OH. You can't really form anything else, it would just be that. There's no room to put an aromatic ring on, because you can't bond it to this oxygen, can't really have 3 bonds, can't bond it to this H, because it's already bonded to a carbon. This carbon's already got 4 bonds, it just won't work. So it has to be this one. So therefore you know, currently the structure will look a little something like this. H3C. So a methyl benzene. And then something to do with, on this carbon, a COOH. Right, now I'm going to specify these 2 groups. This, you can see, is in the range, is about 1.6. And if you look up here, 1.6 is just a hydrogen bonded to carbon bonded to an alkyl group. So it's just basically a regular hydrogen, nothing special about it. You know, there's 3 hydrogens in that environment. So it's going to be CH3 bonded to an R group there. But as you can see, it's a doublet. So this R group is going to have a hydrogen like that, and then something and something. These 2 are not going to be hydrogens. As you can see here, this hydrogen, it's the only one in its environment. It's the only hydrogen bonded to this R. And if you look around, you can see here, there is something that correlates to that. There's only 1 hydrogen in this specific environment. And that also correlates because you can see that this is a quartet, meaning that it's bonded to a carbon, bonded to a carbon, which has 3 hydrogens. And so these 2 basically go hand in hand. But this also means, as it's within this region, it's either this or this. But we know that it has to be on this basically projection here. It has to be a carboxylic acid group somewhere on that. So it's leaning towards this region here. So I would hazard a guess that it's going to be a carbon here. So for example, this one, bonded to a CH3 group there. I'm just going to move this up. And then this C will have a hydrogen here. I'm basically filling in this bit. That CH3 is there, that H is there, that R is this carbon here. And then finally, the final thing we're missing is the COOH group. So COOH. And just check the molecular formula, let's see if that works. So we found it to be C10H12O2. 2 options there, 12 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that checks. 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And therefore that is the final structure. But obviously you could have this CH3 group anywhere, so it could be there, it could be there, it could be there. So it could be either ortho, meta, or para position. But that is the final structure. And if you follow my logic and write down basically what I've stated, then you should get full marks.